Thanks everyone for being here. So today we have Chenru. Chenru completed his PhD at MIT Chemistry and Chemical Engineering. He works on machine learning, decision making, high throughput computation for functional material discovery. And then after his PhD, he joined Microsoft Quantum to work on zero quantum elements as a computation and machine learning solution for chemistry and materials. And then besides research, Chenru likes spending time on building and promoting AI for science, and is one of the organizers of the AI for Science workshops at ICML and GRIPS.
Right. Thank you, Emmanuel, for the nice introduction. I'll go ahead with my talk entitled Diffusion Models on Sampling Rare Events. So before getting started, I would like to thank my collaborators for the research that I presented in this talk. So this talk has two parts. So the first part, I would like to thank Yuanqi from Cornell, Heather and Haojun from MIT for making it possible. And for the second one, I would like to thank Duan, Tianrong, Qiyuan, Carla, and Evangelist for their support. And you may notice that the pictures on the first row is a little bit larger than the second one. It's not because they're more important, it's just because we have more collaborators for the second project. So for the audience of this talk, I will say that we probably all agree that chemicals and materials are the foundations of the modern society that supports our modern lives, and the continuous development and innovation on the chemicals and materials will be a fundamental driving force for keep us going there. And what we are really talking about when we mention stable materials, like the materials that we use, such as the one on the iPhone or like the Mac or even a cup, it will really means chemically that they are the local minimum on the potential energy surface. So the potential energy surface has the, you can imagine that as the x-axis as the atom coordinates and the y-axis as the energy or free energy. Like when we're really looking at the stable material, we're looking at the one that are lying at the local minima of this surface. And besides those stable structures, in chemistry, we also, it's just a subject that really learns how we can study, understand, build, and even control the transformation between different stable molecules and materials. So how we can get from one local minimum to the other is also a very fundamental point of the chemistry study. And along the way, we have usually have a first order setup point, which are characterized as the transition states in chemistry that usually give us the energy between, the energy barrier between the transformation from one state to another, and governs the kinetics of those chemical reaction. To put it into a very simple picture, let's have a SN2 reaction at hand, where on the reactant side we have a bromide species that are attacked by a nucleophilic group. And during the transition state, you can see that we have an intermediate structure that the carbon is kind of bonded to both the nucleophilic group and also the bromide. And in the product, of course, after the successfully attacked, the bromide was detached from the species. And through these two processes, we can see the transition states here have the enhanced energy. And that really gives some of the difficulties in the experiments. So the reactants or products, even though they can exist in the time scale of milliseconds or even longer, because they're kind of stable, and they are long-lived species that can be captured or experimentally studied. If it's amorphous, we can characterize it by NMR to see the chemical environments from it. And if better, we can crystallize those species. We can do the X-ray diffraction to know the exact structure of those chemical species. But for transition states, since they lie at the highest energy point along the reaction pathway, they're really transient, meaning they're picoseconds or even femtoseconds in the time scale, which makes them very difficult to be characterize and analyze experimentally. That's why like those structures, especially their energy difference between transition states and the reactant and products are really important as the rate of the at which the reaction happens are connected by these energy barriers through the Arrhenius equation that shows over here. Basically, it's an exponential dependency. You may see this simple reaction and say chemical reaction is easy. We can use various different methods to get these transition states computationally. But computationally, it's also difficult because the reaction networks, when we really talk about real life reaction, is extremely large. Here I have an example of the cationic rearrangement reaction. So you can see starting from simple three species at hand, when we try to build a reaction network about how those species transform from each other, there are so many intermediate pathways that they can take so that they end up with millions of the intermediate steps and transition pathways across those potential reactants and product. And this is the well-known combinatorial explosion of the possible reactants and products when we build a reaction network, because whenever we get to a step depths deeper in the reaction networks, all the products from the current layer and those that are in the previous layer can possibly become the reactants for the next steps of reaction. And this makes this difficult problem so complicated and difficult. So computationally, people usually use three different type of idea, or like they are kind of interconnected, which are kind of enhanced sampling, metadynamics, and the one that combine them all together, what we call as nanoreactor to build the reaction network. So the idea is that we put the molecules or atoms that we think they will react into a container, and we put it into the high temperature and add some artificial forces to, and then do ab initio molecular dynamics to simulate like its time evolution. And the idea is because we add the temperature so high, and there's some artificial forces, so so some of the species can overcome the potentially high barrier to react with each other. That's the way that we can enumerate potential reactions. And after we do this dynamics, we have a very long time snapshot, and then we can utilize those snapshots where we think the reaction might happen and do a more finer grained path refinement and build the reaction network for further analysis. There's a different approach, which is based on chemical intuition or chemical rules about the reactions, which people have been sure that it has already occurred. For example, those that are enumerated from the USPTO data. The idea is that they first do a brute force enumeration, and then of course the network will be too large to be computed by any like level of theory. And then people apply physical or intuition-based heuristic rules to directly prune the network, get a much smaller one that where the reactions have already been found or like discovered from the past data. And then they do a more fine-grained study on this pruned network. And lastly, they do quantum mechanics or molecular dynamics study to get the rate between the reactions, so that when we start a reaction, we can calculate the abundance and get the final graph. Okay, so basically, those ideas are mostly sampling or enumerating the rare events in chemistry. But the other idea is, can we just learn the distribution of what possible chemical reactions are and then directly sample from this distribution as a marginal? And this idea is pretty much has been applied in the image community from the denoising diffusion probabilistic models, or DDPMs. The idea is that they start with the data distribution, and add forward diffusion process, basically adding noise to the image until we get a Gaussian distribution. And during this process, there is a network really learns how we can transform from the noise without the data to the noise with data at different time step, so that we can also simulate a reverse process with this scoring network, such that we can transfer from a sample joined by from the Gaussian distribution back to the original data distribution. And that's pretty good. And like people may argue that like researchers in and chemistry and material community just apply methods that developed by machine learning people. That's I think somewhat accurate, but like there are still pretty much differences and challenges that we need to conquer in the chemistry. The first is that the symmetry that we have in molecules or materials are quite different from that in materials. For example, the first thing is the SE symmetry that SE3 symmetry that we would like to fulfill in the scoring network. Let's say that we have two space where V is our original molecule space and V prime is the space after the network transformation. Here, I'm just using the cat to represent a molecule because it's cuter. Like we have this function f, which is usually learned through the process. And then like in the case that we have a SE3 operation, let's say D of G, we will, let's say, rotate the cat a little bit, and then we apply the same function f. We will like the outcome, which is V1 prime, going through the same transformation of D prime in the new space. And that's basically saying that if we have this operation graph, when we go through this blue curve or blue direction, and also following along the red direction, we will like the outcome of these two operations by these two formula, which are equivalent. And that's kind of the symmetry that we would like to obey. But that part is usually either ignored or directly simulated by augmentation during the training process. And the second one is the preciseness and the correlations that we have in the data. For example, like in the image community, people usually use the picture of Ian LeCun as an example. I will use that as well. Let's say if we want to generate a picture of Ian LeCun, here I have a model that generated one with the sunglasses, and I don't know whether you can notice that, but like I also add some sprinkle on his face. But I think like in the outcome, if we have this model, we will still see that the generated picture, it looks okay, or even more stylish compared to the original one. But if we do the same for the molecule, let's say we have the same flavor and change some of the atoms or change some of the distance between the atoms, the bound angles, it may make the molecule completely different. It may be good explosive instead of the original molecule that we would like to have certain functions. And another problem, of course, is those molecules are likely to not be able to be synthesized. But besides that, I think from the model perspective, the process is pretty similar. That in the molecule we have the original distribution as the final, like as the one that we targeted for, and we want to add noises in the forward process to make it as a Gaussian at t equals to 0. But like in the reverse process, we just want to use a different model that has that obeys SE3 symmetry, so that we can successfully transfer it back while maintaining the symmetry requirement for molecular generation. And this has been already done by the work the equivariant diffusion model, where they train a diffusion model to generate QM9-based stable molecules. And there also work that generalize the idea a little bit. For example, building the diffusion model to generate the protein ligand complex, or starting with the fragments of the molecule, generating the missing part of them to make a complete molecule. But all of this demonstration, I would say they're constrained at a level where we only have a single molecule at hand. You may wonder why in the bottom two cases, we're still considering as a single molecule because they have, in the first, they have like a molecule and a protein. And in the second, we have different fragments. But I'm saying this as a single molecule because all of those fragments in that later two scenario, they also are governed by a SE3 or like Euclidean interaction. So like when we generate the molecule, we generate them as a full complex, which correlate themselves in the 3D space. But in reaction, they're completely different. For example, we have three fragments or three sets of structures: reactant, transition states, and product. When we see them, like their correlation, they're not governed by their interaction in the 3D space. For example, even if I overlap a reactant and product together, the same reaction should occur. And if I carry them apart in infinitely far away from each other, the same reaction also occurs. That's how we write down the chemical reactions into chemical formula without mentioning their 3D orientation with each other. That's a unique symmetry that we need to bear in mind when building this model. But besides that, I think everything else is pretty similar from generating a single molecule compared to generating three molecules altogether, where we just add noise that are independent to three structures and make them to be Gaussian-like in the future as a product state for three Gaussian distribution. While in the reverse path, we use the scoring network to denoise them to get the original data distribution. Okay, well then, like I already touched a little bit about the unique symmetry, which we call object-wise SE3 symmetry. What does it really mean here? I'll just make a very simple example to demonstrate. Imagine that we have two molecules like this. One of them are reactant, one of them are product. If we do the system-wise SE3 transformation, here I just rotate them altogether by an angle through a axis. We should imagine that the forces or like the vector field on these molecules should rotate accordingly. And if we do a non-SE3 transformation on them, let's say we just completely change the bound angle of a molecule such that becomes a different reactant, then we should expect that in both scenario, SE3 and object-aware SE3, the vector field completely changes. Like basically there's no simple relationship between the vector field from the new set of molecule compared to the old one. But if we do a object-wise SE3 transformation, let's say we only rotate here, I only rotate the water molecule without touching the ammonia molecule, but also translate the water molecule a little bit. In that case, if we consider the SE3 simulation, like symmetry, we will get the similar idea, we will get the similar outcome from as the non-SE3 transformation because it broke the graph directly as the SE3, like they will think these two molecules are one part and they're connected by the 3D space. While in the object-aware SE3, these two objects are considered separately, and so that like the force from the both of them subject, like the water and ammonia, they also only change accordingly with respect to the change of the SE3 transformation. Here, particularly ammonia without any changes, and the vector field on the water will have a certain rotation as it has been rotated. Implementation-wise, what we have is the following input, where we have a set of graph characterized by the edge and the null vectors and the null features. what we do is that like we put it into an equivariant block, which is similar to all like you can choose an equivariant model that you like, maze, equiformer, whatever. And then we just let each of this subgraph go through this equivariant block one by one and generating those equivariant feature. What we do is that we then scalarize the equivariant feature that are potentially have higher order tensor in it, such that we get a final scalar. And we concatenate the scalar and letting them go through the scalar-based message passing network. And in the end, we only get the output from the message passing block to the equivariant block, but only replacing the zeroth order, which is a scalar part of those equivariant feature. And we do this one time and another. And in the end, we just read out the final outcome. And this simple trick in this like in this change of the network architecture, basically apply all type of the equivariant neural network and will automatically fulfill the SU3 symmetry, because when we do the all atom-based message passing, only the scalar-based information are passed through and interact with each other without the touching of the higher order tensor, which may correlate them more in the 3D space. At the first demonstration, we're generating chemical reactions from scratch. So here we assume that there's only CNOH 4 atoms in vacuum, and we use like the model that we developed, which called OA reactive, to generate those possible elementary reactions. So from a chemist perspective, I think these are all quite reasonable reactions, including those from hydrogen transfer and also the one that opening the rings to form the line-based structures. But one thing that we want to focus a little bit more is the transition state search, which is a traditional optimization problem. Because we see that like transition states, a little bit recap, is the highest energy point that connects the two like the reactant and product together, and it lies on a path, which we call minimum energy pathway. Along the path, all the perpendicular force are basically zero. Traditionally, there has been a lot of development along the transition state search problem. For example, like the string method, growing string method, and natural elastic band. But all of them require hundreds of the energy and gradient evaluation, here particular with density function theory. And it will take hours or even days to complete or fail for typical chemical systems. So here, like since we already learned the whole entire distribution of the chemical reaction, we can make transition state search as a conditional generated task from this diffusion model. What do I mean? So here I'm just using an example of the cutie animals and their fruit fruits. So let's imagine that we have a series of pictures that has dogs, cats as the input from the animal side, and we have the foods, for example, meat or fish in this particular case, as the plausible pet foods. And like in all of the picture, we have dogs paired with with meats and cats paired with fish. And in the case, we learned the joint distribution about this, about the cats and foods, pets and foods. And whenever we give a new past picture, for example, here I get a samoyed. In this case, the model should automatically, because it's seen so many of them, it should generate a meat paired with this samoyed as a dog. And similarly, like we have this idea of the reactant products and transition states, we also put them as a joint distribution when the model learns it. But when we really generate a new molecule, we'll just put the reactant and products as the condition such that it will automatically get the marginal as the transition states. So how well does it work? Okay, it works well for smaller molecule generation. For example, here is a five-member ring opening reaction and forming a 3-member ring. Out of the 128 rounds of the OA reactive, we see the majority of them have a generates a transition states that are pretty similar to the true transition states with very minimal change in the RMSD. However, we can see there's still very few cases where we generate different a structure that are different compared to the true transition states, even though like they also are the saddle points on the potential energy surface. And for reactions that are a little bit more complicated, we can see this behavior is exaggerated in the case where we sample more diverse transition states, even though we can get the final true transition states occasionally, but like in many other times we will get more diverse transition states. It's good and bad in two senses. So it's good because it will help us to get unintended reactions, which will be very important when we generate the full reaction network, where even experienced chemists have no idea what it should look like. It's bad in the case that here, since we already have a pair of reactant products, the transition state should be unique. To bypass this issue, we build a confidence model. Basically, we have the reactant products and the generated TS transition states as a pair, and we put it into a model that is share the same architecture, the scoring model in the diffusion model, but just swapping the output as a binary classification layer. And we get score for each sets of the structures with different generated TS. And then we have different scores. And in the end, we just pick the score that is the highest as our final recommended structure. And from the outcome, we can see that the recommender always picks at least reasonable transition states conformation, which can be seen as a really dense population on the bottom right part of this graph, where the recommended TS has really high confidence, where very low RMSD compared to the true transition states. And here is a graph basically showing the accumulated probability of the structures. So we can see that most of the time we can get the transition states that are pretty close to the true reactant. At least 75% will have RMSD smaller than 0.2 angstrom, which are pretty indistinguishable, I would say, from the eye. And of course, there are also very high difference transition states as well. Another point that we're interested in is the rate at which the reaction happens that correlates to the energy barrier between the generated transition states and the true transition states. So here I have a graph showing the x-axis as a RMSD between the generated and the true transition state, while the y-axis is the energy difference between them. So we can see that they kind of have a linear correlation in the log scale, which means that there is a power law dependence in their original scale, but we can see there are some of the scatters around. So for the first one on the top left, it has a really low, relatively low, I would say RMSD. If you see these two structures, they don't differ that much, but the energy difference is 50 kcal/mole. I first don't understand it until I did a linear change between the true transition states, basically linear interpolation between the true transition states and the transition states that are generated by the diffusion model. We see there's a very steep discontinuous behavior in the energy difference. This means that they, in the electronic structure, basically calculation in DFT, they converge these two structures into two different electronic states, giving very different behavior. So that's something that we should ask help from the solver of the quantum chemistry instead of from the model. And on the right, bottom right, we see cases where you have really large RMSD, so the structures are quite different, but the energy difference is pretty low. So here's only 0.5 kcal/mole at around like 0.8 angstrom difference in terms of RMSD. The reason is that there's some of the structures, transition states, where they have different fragments. And we can see that in this case, even though we do not generate the correct alignment between these two fragments, the geometry of each fragments are pretty accurate, and the interaction between these two fragments is so low. So basically, no matter which orientation that we would like, they will also have very close energy. That's why we get a lower energy here in the graph. And basically, okay, we can see that from one-shot generation, the model is already kind of accurate, but by adding the recommender, like you can improve a little bit more by now choosing the structures that are highly inaccurate, but still, like it will be, of course, if we were able to get the best of the samples that we generated by the diffusion model, the accurate, like they will be more accurate. Okay, so this is only one part of this talk about using diffusion model, but like when I see this, like then people are using a different like technique called Schrodinger bridge on generating new images. The idea is that we do not start with the Gaussian distribution. Here we start with a, let's say, a distribution where the image is simply blurred by the systematic way, and then we just try to restore the image. In that case, we're now transferring a distribution from Gaussian to a target distribution. We're starting with somewhere closer to the final target. And this can be the effect by starting with a simple like close target distribution can be manifested by the figure on the right, where the vector field learned by the in the diffusion case, where we start with Gaussian, is more difficult and the uncertainty is higher compared to where we do a transport from a distribution to another. And in chemistry, we actually have that prior knowledge as well. So in the diffusion model, we actually just learned the joint distribution of the reactants and products and transition state, where we originally transformed them from our Gaussian to the joint distribution of the elementary reaction. And in the reverse process, we do the stochastic denoising, where like each step is stochastic. That's also why in the end, in the transition states, we may generate different structures at different trial, even though that we start with the same exact reactant and product. But in this problem, we have a better prior than now. That is just the linear interpolation between the reactant product, just the reactant structure plus the product structure divided by 2. And in this case, we can do a deterministic inference, meaning that we do not change the reactant and the product along the time axis. And for the transition states, we only change them linearly from this from this linear interpolated initial gas of transition states to the final transition states. This idea is kind of in analog to the dynamical optimal transport. That's why we name these new methods as react-OT. We can see that the react-OT gives better performance in terms of both the structure similarity measured by RMSD, as well as the energy difference, like the barrier height evaluation from this cumulated parabolicity curve. Especially, we can see that react-OT can give a higher fraction of molecules being very accurate in terms of the barrier height, as can be shown this difference between the orange curve and the red and blue curve in the low energy area. And the good thing about OT is that first, that we start with a closer distribution compared to the target. So the transformation is easier in essence. And also, because we only take the linear path, the number of the sampling steps, or like the number of function evaluation is much smaller compared to running the the diffusion model. So in diffusion model, we usually still takes like 150 or 200 steps to get a molecule, a stable molecule being generated. But in React OT, we find that we only need 6 steps in terms of getting the generating a structure that are converged compared to using a larger number of the like number of functional evaluation. That gives 50-fold of acceleration compared to the single shot reaction like the diffusion model. And because like in diffusion model, we want to have a more deterministic flavor of the final generated structure. So we use recommender. That kind of increase the number of sampling or the number of calls of the diffusion model even more. And that makes the inference time even higher. Like in our case, since we run 40 shots, that's 40 times higher than the single shot model. And like that will since the React OT is the sampling process is fully deterministic, so we only need to run it once and that's it. Like the outcome of the React OT will not change. That makes the sampling process a much easier to implement and also less costly in terms of time. And we can see that the MEE on the barrier, both the MEE on the barrier and the RMSD in terms of structure similarity is also higher in terms of the accuracy for React OT. And here is a final comparison about the models. We can see React OT gets, I would say, 20% more accurate compare like the diffusion model with recommender approach. And of course, much faster in terms of inference time. And we also tried different things that I will not get into the detail, but the idea is that we add some pre-training to a much larger database that is not built by DFT, but a lower level of methods, semi-empirical methods, say XTB. And we find that after this pre-training step, React OT can further improve 25% in both of the RMSD and the barrier height. And like since here we have a setup where we still need to know the reactant and product in terms of using the generated model, but originally, like all the previous evaluation, we still assume that we have the DFT optimized reactant product, which may be expensive or sometimes impractical to obtain. So here we also do another experiment where we swap the DFT optimized reactant product with the XTB optimized one. Even though the reactant products optimized by different level methods still show quite difference in terms of their geometry. We find that the React OT does not deteriorate that much. So the model performance only dropped by another 10% in terms of the performance. I think that will be a very good sign of adding pre-training as well as using more realistic, simple inputs into the model and make it more powerful in terms of the practical application. So just in the end, a summary of the talk. So the first part, I talk about OA reactive, which is a diffusion model that simulates the joint distribution of the reactant and product, where in the end, we can use conditional generation to generate the TS given the reactant and product. So here I post the link of the repository with the live demo. So if you want to try, go ahead. And for the React OT, we've further formulate the transition state search problem as a transport problem with Schrodinger bridge. And we made use of a better prior compared to the Gaussian distribution as the initial guess of the transition state, which in the end makes the transition state generation a much faster process with higher accuracy. And like this work is still like under preparation. We're trying to draft it pretty quick, and I will put the preprint link under the page for this talk in the proto as well. I think that's all, and thank you all for your listening, and happy to take any questions.
Great. Thank you, Chenru, for your talk. Yeah, if the audience has any questions, feel free to raise your hand, type something in the chat. I guess I can start with a maybe open-ended question. So you've trained these models on data sets generated from simulations. Do you think the next step is to kind of train the model directly on the energies and the local simulations?
Yeah, that's a good point. So like in part of this work, we also find the similar model can be used to predict the barrier directly without without doing explicit DFT calculation. Basically, like in the current model, since it's a scoring network, we predict the noise or the vector field being added to the structure, but we can simply swap that last layer as a simple scalar output layer, which can then predict the energy. I think the performance is quite good, but we just omit it in the paper because it's our we want to focus on the structure generation. But that's indeed very important part to also consider in the practical application. Yeah.
Thanks. This is a follow-up to that. So if you train a diffusion model, typically it will kind of concentrate the probability around its training set. You did mention that the model did generate transitions that were wrong, or not interesting ones that you have to then filter out. Is that something that's actually desired? Would you want to have a multimodal kind of outputs where there is, you're talking about this at the beginning, there is an explosion, combinatorial explosion of possibilities.
Yeah.
That's something that you'd be interested in, but you don't have the data for?
Yeah, that's a really good point. I think in terms of the final application, so here I only demonstrate the application at which we can easy to evaluate. For example, I have the certain reactant and product, and I have the data set so that I know for sure what the true transition state is. And then I want to compare whether the model can generate the correct confirmation of the transition states. But sometimes in the real application, especially for reaction networks or reactions that we do not know the mechanism for sure, it more requires a flavor of exploration than just generating the correct transition states. In that case, I think we should make use of or take advantage of the diffusion part where it can still generate reactions that are unintended or undesired, putting away. But those are still correct transition state in the sense that it fulfills the saddle point requirement on the potential energy surface, then we can just do further calculations, for example, intrinsic reaction coordinates to get the reactant and product corresponds to the generated transition state, even though that is not desired, to make the network more complete. In that sense, we can basically build a more complete network so that we won't, we have a lower likelihood to miss part of the potential side reaction or the reaction that are dominant in terms of the reaction network. Because now, when we talk when organic chemists or inorganic chemists, when they propose mechanism, it's always driven by chemical intuition. I think the diffusion model in the sense will complement their chemical intuition just in case there are reactions that are not in their mind that will actually happen.
Yeah, that makes sense. Cool. Yeah, any last questions? Yes. I can read it out loud. So considering that not every chemical reaction can be studied with every level of theory or every basis set, is it necessary to construct case-specific models for different types of reactions?
Yeah, I think that's a good point. I didn't go through every single detail, but in the pre-training part, what we find is that DFT is, of course, a little bit background. DFT is extremely costly in terms of calculating the reaction path because in order to get those final three structures that we use in terms of training, it needs hundreds of thousands of evaluation of a single point. And XTB, semi-empirical method, is much cheaper. It's 1,000 times cheaper. So we can basically get we have the capacity under the same computational resources to get much larger XTB data set for the reactions compared to DFT. And what we found is pre-training on those XTB level theory data indeed helps in terms of fine-tuning the model on the final target, which is the DFT data. And I think that's right. I mean, like if we have the computational resources, I'm now biased a little bit to run it on the lower level of theory of interest to first get a, let's say, pre-trained model for more type of reactions in mind. And then like when we try to study a particular reaction, we just need to get a smaller number of data for that. I think that's kind of my current take from the experiments that we did.
What was the so from the practitioner's point of view, what was the compute required? Did you use CPUs or GPUs only?
Currently for DFT and semi-empirical method, I think the majority one are implemented on CPU, even though there are trends moving those expensive ab initio calculations on GPUs. And for the models that we use here, so the scoring network of both OA reactive and React OT are trained on GPUs because they are graph neural networks that are more efficient when using GPU compared to CPU.
Okay, the SC3 might have higher cycles. The SC3 transformations might have higher cycles as compared to the other stuff. So I was wondering which part of your uh, uh, pipeline had the highest uh, uh, compute requirements, as in, yeah, which part, yeah, if you
Yeah,
get
that's a
my.
very good question. So, because like all the ML models, even though we're talking about how we can accelerate it, it's already pretty fast compared to like ab initio calculation. So without like in the original workflow where we still need to have DFT optimized reactant and products as inputs, there's no doubt that the DFT optimization of the reactant and product will be the most expensive step. I would say it's thousands or hundreds more expensive than the ML part. But now that's
Mhm.
why, or like that's which motivates us to basically use XTB, React, and products as the input in this workflow. Even that, XTB is 1,000 times cheaper than DFT. XTB is still the like XTB optimization of reactant and products still I think take on average 6 seconds, which then becomes the most costly part of the workflow because React OT only takes like below 1 second. That's why I think in like later on, we probably just want to use ML fast field to optimize that. That will also like optimize reactant and product. That will probably lower the cost a little bit, but like yeah, usually providing the inputs since we're talking
Yeah,
about ML workflow will be the most expensive part.
yeah.